Okay, so do you guys watch the last Friday lecture? Okay, perfect. So what we left on Friday, we tried to do some nomenclature on cycloarcane. So for example, if you have this ring structure here, you can try to count the carbon. 1, 2, 3, 4, and 5, 6. So basically, it's pretty much the same what we did for the, arcanes in the chapter 3. There'll be hex, right? And there's all single bond, so it'll be A and E. And but this is in a ring structure, so we're gonna put cyclo. So we call this cyclohexane. Whenever you have some substituting groups, methyl here, or you have another methyl group here, we just try to put, we try to count the, maybe I'll put it here. Okay. So we can try to count the carbon so you can get the lowest possible location, locant for these two substituting groups. So instead of counting carbon from here, that will give you 1 and 4. But if you count it from here and clockwise, 1, 2, 3, right? So this is, I'm sorry, this is better. So we're gonna do 1, 3. There are 2 methyl groups, so we dimethyl, cyclohexane. Okay? So this is the pretty much the same that we did for the arcanes in chapter 3. But make sure you guys put cyclo. Okay, that's pretty much it. So cyclohexane. The one I didn't cover on Friday was the whenever you have some groups like maybe it's not a methyl or ethyl group, but it's more like a bromine or chlorine, sort of the halogen group there. So whenever you have this type of the atom here, you can try to consider as an alkyl group. So what you can do is you can always try to get the core name of that element. So bromine, we're just gonna put bromo. Okay. So if it's chlorine, you're gonna put chloro, and so forth. Okay. And then we can try to. We also have a methyl group here, so you have a methyl group here too. And please remember, whenever you do, either count the carbon from here or here. It will be either 1 and 3. 1 and 3. Same. So the question is, where should you count the carbon from? And you need to follow the alphabetical order. So it will be B comes first, then M in alphabetical order. So we're going to count the carbon from here. So this will be 1 bromo, okay, 3 methyl, and cyclohexane. Okay, it's not going to be 1 methyl, 3 bromo, cyclohexane this one. Okay, because of the alphabetical. So if we change this to maybe chlorine, it could have been what? 1 chloro. Yeah, perfect. Yeah. That's pretty much it. So make sure you guys try to. When you try to find the some cycloalkanes, see if your ring structure is like a dominant group, like a parent group. So we can use this one. If you have some substituting group is bigger than your ring structure, you may have to do it the other. But this is the pretty much the last part of the nomenclature in chapter 4. Sounds good, right? So let's move on. Okay, here's the thing. Since we have a ring structure, we have think about some other different type of force that we didn't consider from the arcane. So whenever you have maybe ring structure here, okay, and then they are in carbon, 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 right? Can you guys actually name this one? There's a 3 carbon is probe, right? Probe. They're all single bonds, so it'll be propane, right? But this is a ring structure, so it'll be cyclopropane. Perfect. It sounds good, right? Perfect. You guys doing so great. So if this is the case, there's one thing I want you to recall from Jenkins 1 and 2. So technically, what they're doing is they have a bond to 2 other carbons from here, right? And there is also 2 bonding to other hydrogens over here. Okay. So technically, if you go from the Jenkins 1 and 2, the carbon is group 4, right? Group 4. So this one can have 4 single bonds. Okay. So that means here's the thing. If you draw the carbon with the 4 single bonds, it looks like they have all bonds on the same plane, like you saw on the bondings on this plane of the blackboard here, right? But technically, when you think about the space, that is not 2D space, right? Obviously, in reality, we live in 3D space, right? So if we have a tetraplanar like this is a waste of their space, because they have other plates only here on the back of this ball here. So what they do is they do more like a cross, but they rotate and kind of spread on the boards. So what they do is they try to do some like tetrahedral structure, so they can have a more efficient spacing for 4 bondings 3D. Makes sense? So it's not going to be 90 degrees here. It's not going to be 90 degrees, right? Does it make sense? This is 3D, it's not 2D. So you have to kind of make it better way. So this one, once again, if you saw the last lecture, this is the one that goes forward here, and this is the one that going back. So it's like this, this, and this. Okay? So technically, the bond between these two is actually 109.5 degree and all, not 90. So first you get tetrahedral structure. Perfect. So we call this tetrahedral structure. The 4 bondings nicely spaced out in the 3D structure. Okay. So if that is the case, if you think about the degree, the angle inside the triangle, propane, cyclopropane, this will be all 60, right? 60 degrees. But in this case, those bonds are forced. They're forced to make a ring here, right? 3 carbon member ring in force, right? And then they're going to have, there is no way you can twist much on 3 carbons on the ring. So that means you have to kind of squeeze. You need to kind of force to the bond set to the 60 instead of 109, right? So that means, obviously what happened? This one will resist, right? This is the bond angle they want to have naturally, but they're forced to have a smaller angle inside in the ring structure because of the nature of the triangle. It's inside always 60 on each, right? Does it make sense? It has to be 109, but now it's 60. They gotta do 60 now. So they're forced. So they're going to experience a certain amount of what? Energy. They need to have a certain amount of energy to do so. This is what we call literally angle strain. Because of the angle. So the last one we talked about was torsional strain, because eclipse conformation, stagger conformation. We also talked about the static hinderness because of the proximity between 2 groups on each carbon. And also this is another one, the angle strain, because of the angle they need to sustain in the form of the ring structure. So they have to do some extra energy to require. Okay, so that is a very extreme case. Obviously, butane as well, right? They're all in like 90, but here's the thing. From here, it gets a little better because the only thing, the carbons are on the same plane is cyclopropene. But from number 4, 5, 6, 7, 8, they still have they have a more room to they can move up and down. So it's not totally on like a plane, but semi. So they'll experience the less amount of the angle strain than the cyclopropene. And it goes on the cyclopentane. We have, and also the bond angle is a bit closer to their to their original like tetrahedral angle too. And then also they can kind of move up and down because they now have more members in the ring, so they have more space to kind of move up and down. So they can adjust their bond angle somehow in a certain degree. So they still also experience the angle strain, but not as much as they did in cyclopropene. I know it sounds good so far? Okay. So now we're going into our main structure. This is why in chemistry we find this, we also talk about in very detail because of a special nature of this one. So what about this one? Okay, so there has to be about this degree. So this also may experience some angle strain, right, based on this one. But when we did the experiment, it has almost zero angle strain, and also almost zero torsional strain either. So here's what happened. If that is true that this will experience type of angle strain, because it has to be 1 and 9, but it's bigger than 1 and 9. And also, but if that is only true when all carbons are on same plane, right? Then that makes a much bigger angle than 1 and 9. But if it's not in the same plane, they can, like I said, they can always go up and down. Can you guys guess why we did this thing in the plane? Not just for the angle, but like I mentioned earlier in chapter 3, what about good about the single bond is what? They can always either rotate and move. So they can actually change the angle by going up and down. Like they can rotate the bonds where they want. So it's continuously moving at a certain conditions. If there's enough energy, they can always okay to move, and they makes type of certain conformation. Okay, and then interestingly, all the carbons are here going to have all stagger conformation here. So there's almost no torsional strain. That is why this will make this cyclohexane so stable. So stable. Because there's no angle strain that we expected because it was not on the same plane. So the bond between those two, angle between those two carbons are actually very close to 109. Very close to 109. And also they're all in the stagger. So if you look at this top to bottom, right? If you look at this to side view, if you put this on like in the side view, and you're looking at through each directions, they're also all staggered. So that means there will be almost no torsional strain. That is so what this cyclohexane is unique about. So stable because of these two. And also they're going to experience very low steric hinderness as well. because of staggered conformations and the angle structure. Okay. So this is why we think the cyclohexane is so special. Okay. So here's the thing: if it is so special about this one, okay, and now it's because it goes up and down, it's a conformation change. Then let's talk about what it actually looks like. Okay. So the most famous one is the chair conformation. That is the stable form of the cyclohexane. So there's several tricks you can try to do. Is this? You can try to draw some like lines, like in a tilt line over here, like this, and you can try to estimate that this like a wave, like a linear wave, and just put the point there. Okay. And same here. You have two lines. Pick the lower one and do the trajectory here to get a sort of like a wave, linear wave, and put the point there. And all you need to do is connect those dots here. Okay, that's the first step. Okay, so whenever you have this one, all you need to do, you see this one, this point is pointing down. Do you see this is pointing down, right? So you draw the line going downward. Okay, you see this line, this point is going down. It's a point here. Okay, and this point here is also going down, right? So just like this. Okay. So the one that is pointing up, just put upward, like group over here. Looks like this. Okay. And then from here, what you can do is, oh, by the way, so the first thing what you need to do, I mean, you don't have to do this one first, but I mean, if you want to do it. So you can do down, down, up, up, up. As you can see, this is indeed stagger, right? Down, up, down, up, down, up, down. It's indeed stagger. If you look at through here, 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 here. Okay. Anyway, and if you go for up or down, we call this axial group. Axial group. It means axial. It's like an axis, like a y-axis, and a vertical axis. Okay. Then what we need to do next is we're gonna put some equatorial groups over there, which is also pretty much the same. Do you see this line here? Is the parallel to this line? You go this and do in the middle. Okay. This is the line here. The two lines here, here, and here in the middle. Okay. And if you look at those line here and here, right? So you can try to do here, and this line here, and here. Okay? Oh, sorry, I just drew too long. And then this line here, right? Goes here, here, here. That's it. It's sometimes very hard to do, but this is what you can do. So obviously, what you can do with this one, like I said, they can always go change by moving their status, the rotation. What you can do the other way is they can also do up and down. So we're gonna go do another one, another chair. So I'm gonna do the same here and here. It's like here, okay. Do here, here. Okay. There's the same thing, but in a different form. Okay. So you can do the same. Go up, right? This is down, up, down, down, up. Do you see this? The pointing down, pointing up, right? And then same thing. Just feel the equatorial groups right here, here, okay, here, here, and okay. So this is go in this way or this way, back and forth. Okay. This is how you can do the chair conformation. So here's the thing. It doesn't mean that this is. It looks like a G, right? But it's because you're looking at this one from top side view. So this is still this one. So let me explain this one. So if you have this type of paper, you can try to fold on the side with here. So I'll show you. So if you have this shape, secondary shape paper, try to fold here. Fold these two like this. Try to fold top and bottom. Okay. So it looks like this, right? Like this, right? Okay. And then just try to fold one side the other way. Like this. Like this. Okay? Alright? And then if you try to look at this one to your side, bit of up, top position and side, and see what it looks like. It looks like this. This is why. So this is this, not this one. This is because we have to draw it from the top side view, and this is what it looks like, this. So obviously, this also tells you, if you look at this from the side, it's not plane. If it's plane, it would be like this. But it's not plane. It's like this. That's why it looks like this. Do you see that? See, from the top side view. And also, when you go from here to here, only thing you have to do is fold those two sides in the other way. So now this is up. Like I said, this goes up, right? So now this side goes up. And now this part will go up. The other part will go up, and this part will go down. And you actually go in, fold it in different opposite way. And if you try to look at it from the top and side view, it looks this one. Does it make sense? You good? Okay, great. All right. So here's the thing. Whenever you look at this one, this is the sort of things you can draw from this cyclohexane. So maybe you can try to do something like this one. On your exam, this is very famous questions. So we're assuming there are in the hydrogen, right? Okay. But if there are hydrogen, as we know, the one assumption we can do is what? You don't have to show the hydrogen on the skeletons. So we're just gonna what? Just remove this one. Doesn't right? You normally show the hydrogen, right? Hopefully you got this impression by now. Okay, so if it's all hydrogen, you don't have to show. Okay, but if you have some special group like methyl group, bromo, chloro, anything, so I can put methyl group here, then I need to show here. Okay, so maybe not even this, like this. Okay, well I'm just gonna put methyl group here, and then whenever you do, so still think about this one as a paper like you just folded today. When you go from here to here, all you need to do is go to like this, right? We fold it in the opposite direction, they go up and down by rotating the single bond, right? So then you can assume there's a hydrogen here, okay? And this one will now, like your paper, it folded now, not upward but down, right? Then here it is going to be down and the equatorial. So if you look at this one, you might be able to know, oh, there's a methyl group now in this folding. If you fold the paper in the other way, or go in equatorial group, not exit anymore. Because you change the way it folds, change the way, like on the up and down. Okay. So this is something. So here's the thing. If we had, for example, I'll give you one example. So if I put the one chloride here, okay, then can you guess if chloride will be here or here? It's now in the paper is equatorial, right? But you're going down. So it goes where? It will be still equatorial or in the down? Because you make it the other way. So it will be down, perfect. Yes. Here. Okay. Makes sense? So I know this is sometimes if you do it for your first time, it might be some, maybe this is a bit weird, but only thing you really need to do is try to look at it as 3D. So if you feel like it's better, you can also make a actual 3D structure or the paper, you can try to fold it. So this is why we call this like a chair. So it looks like a chair. Chair you can just sit on, like here, chair. Okay. I hope that makes sense. Probably later, I'll do some more later on Wednesday. But this is how you can get this chair conformations go to here, and we're gonna call this ring flip. Okay, so just like you're just flipping the other way, so you can have this type of the chair conformation change, conformational change. Okay, can I move on? Okay, so I'll move on. You can practice with the paper or any other 3D model if it's really hard to see, and the 2D paper, right? It's very hard. So just try to leave a bit of practice on, the real examples. So there's one more thing, couple more things I actually need to mention here. So sometimes what they do is they do this one. Okay? So I'm not gonna cover in very detail, but this is what we call bolt conformation. So here you fold it like up and down on each side of the paper, right? But here it will be more like same side. So it's like a bolt here. Okay, it's like a bolt here. It's literally like this, but still it's not looks like this, but it's still just this shape. We're just looking at in the top side view, but it's now folded in the same side. That's the only difference. So obviously, can you guys guess which one will be more stable or unstable? This one will be unstable, perfect. Because you're going to have some groups on here as a closer distance will experience static strain, right? Because of the size and the proximity will cause some, kind of a discomfort I mentioned before. And there's certain amount of energy required to sustain this one, and also on this part of the carbons will have a more like eclipse version, not rather than staggered. So this is more unstable than this one, which chair conformation most of the time this is most stable conformation, but this is not really. This is very quite unstable. There's one more state that is more unstable than this one, but I'm not gonna mention it today. So anyway, so this is less stable than this one, or you can say more unstable than this one. So what they do by just a little effort to slightly more stable is twisted board conformation. That means, so if you do this, right? If you do this, there will be static, steering, right? So if you just not in the same way, but twist a little bit, like here, twist like a little bit, right? Then those static hinderness will be less because the distance diagonal direction will be larger than linear, right? So they'll experience like a less static hinderness, And axial eclipse conformation will be a bit more slightly tilted and small degree, right? So twisted board conformation is just slightly more stable than just regular board conformation. That's all you need to know. That's it. I'm not going to cover the positioning. This is the only thing you should know for just what might be the other conformation that you can get from the just a 6-member ring arithmetic structure that is board system. But this sometimes at certain special conditions they can have a little more like a flexibility to make themselves a bit more stable. Hopefully that makes sense. We good? Okay. All right. So that is pretty much it for the chair conformation. Okay. All right. So let's move on to next part. This was the. But it all makes sense, right? Do you have any? Okay. I'll just move on then. So the next part. No. So. Okay, I think. That's pretty much the lecture. All right. So I'll just stop here today, and then I'll try to cover the later part of chapter 4 on Wednesday, and then we can try to start on the chapter 5 on Friday. Okay. So hopefully I can finish the chapter 5 by next Monday, and I'll try to keep the Wednesday and the Friday, next Wednesday and Friday for review, and also a little bit of chapter 6, but not a lot. Okay. All right. Thank you, guys.